Welcome back. So, if you caught our precision versus recall explainer, you probably remember that tricky threshold, right? The whole balancing act where you trade one metric off against the other. Well, ROC-AUC is basically what happens when you stop picking just one threshold and decide to look at literally every single one at once. I've got Techie here today, our little silver gray metallic robot with the glowing cyan eyes, ready to help guide us through this. Okay, let's dive right in and see how evaluating performance across all thresholds actually works, and, why it's a genuinely massive game changer for your machine learning projects. All right, section 1, how it actually works, zooming out to the macro view. To start us off, let's do a super quick refresher on the groundwork we laid last time. A classifier doesn't just output a simple, definitive yes or no. It actually outputs a confidence score. And the threshold, that's the exact line in the sand that decides where yes actually begins. If you slide that threshold way up, the model gets much stricter. What happens? Well, you get higher precision but lower recall. On the flip side, if you slide it down, the model gets looser, giving you higher recall but your precision takes a hit. It's the classic trade-off. But remember, that trade-off is only happening at one single snapshot in time, at one very specific threshold. So instead of just picking one single snapshot and reporting one precision and recall number, we're going to do something much more comprehensive here. Step 1, we take that threshold and we slide it through its entire possible range. Step 2, at every single position along that range, we plot two specific numbers. We plot the true positive rate, which, by the way, is exactly the same thing as recall, on one axis against the false positive rate on the other axis. And false positive rate is just how often the model wrongly flags something that wasn't actually positive. Finally, step 3, we just connect all of those plotted points together. And connecting those dots brilliantly illustrates the whole picture. We get the ROC curve. This is literally a curve showing the complete, comprehensive trade-off across a model's entire range. By plotting the true positive rate against the false positive rate, you aren't just looking at one isolated threshold snapshot anymore. You are looking at the entire landscape of the model's decision-making power mapped out completely. So the absolutely crucial question is, how do we actually measure and quantify that entire landscape? Enter AUC. That stands for the area under the curve. It provides a single number, ranging from 0.5 up to 1.0, that completely summarizes the model's overall separation ability. It is quite literally just the measured area sitting right underneath that ROC curve we just talked about. It takes all that complex threshold data and neatly boils it down into one single qualitative score. Let's break down what those specific numbers actually mean for a model. A value of exactly 0.5, that means the ROC curve sits right on the perfect diagonal. And what does that tell us? Well, it means the model is doing absolutely no better than randomly guessing, literally. Regardless of the threshold you pick, you aren't getting any real predictive value. The true positive rate and the false positive rate are just rising together at the exact same pace. Conversely, think about what happens when the value approaches 1.0. The curve bows sharply toward the top left corner. This indicates incredibly strong class separation. It proves the model is genuinely separating the two classes well across virtually every single threshold you could possibly pick. It's keeping the false alarms low while hugging super close to a true positive rate of 1. That top left corner, that's the holy grail. It is exactly where you want your model's curve to be. So why is this particular metric so incredibly powerful? Well, the genuine power of AUC is basically threefold. First, it completely summarizes a model's overall ability to rank and separate classes. Second, it requires absolutely zero commitment to a single specific threshold. And third, because of that, it measures the true underlying separation quality of your model. That is exactly what makes it fundamentally different from precision, recall, or F1, which, all heavily depend on wherever you just happen to draw that line in the sand. Moving right along, section 2, a real example, Model A versus Model B. We've got Techie making a second appearance here to help us transition from theory into practice. Let's dive into a real comparison. Consider Model A. Its curve bows sharply toward that top left corner, hugging close to a true positive rate of 1 while successfully keeping the false positive rate super low across almost its entire range. Then, you've got Model B. Its curve just sits right there close to the diagonal line, meaning that at literally any threshold, its true and false positive rates are just rising together completely pointlessly. And this brilliantly illustrates the real-world difference in a clear breakdown. Look at Model A. It genuinely separates the two classes well. Because it correctly ranks positive cases with higher confidence than negative ones almost universally, its curve bows to the top left, giving it an AUC estimate near 1.0. It's a strong, genuinely reliable model. But then look at Model B. Its separation quality is basically random. Its shape hugs the diagonal, and its AUC sits right near 0.5. Its confidence scores simply don't meaningfully separate the classes at all. In fact, to sum it up perfectly, Model B is barely better than random guessing. It's essentially just a coin flip wearing a machine learning costume. Seriously, a random negative case is about as likely to get a high confidence score from Model B as a random positive one. Which brings us to a very practical question, one that you should absolutely always ask. Why does this actually matter in practice? Why go through all the trouble of mapping out every single threshold instead of just looking at the one we plan to actually use? Well, here's the reality of building these systems. You might not know your exact production threshold yet, or you might want to compare two candidate models, like Model A and Model B, fairly before committing to one. Precision, Recall, and F1, they evaluate one specific chosen threshold, but ROC-AUC evaluates the general quality across every possible threshold. AUC doesn't replace those other metrics. It answers a genuinely different question altogether. It lets you evaluate fairly without being tied to a somewhat arbitrary threshold choice during your testing phase. But the crucial point here is understanding the limits of AUC too. It is absolutely perfect for understanding general model quality and comparing models side by side. However, AUC won't tell you exactly how many false alarms you're going to get at the specific threshold you actually ship with in production. For that operational, day-to-day reality check, you still absolutely need your precision and recall metrics. Think of AUC as your overall macro view, not the operational micro view. Okay, let's wrap this up and recap how all of this builds our final understanding. First, a classifier's threshold decides where yes begins, and sliding it trades precision for recall. Second, the ROC curve plots that entire trade-off, true positive rate against false positive rate, across every possible threshold all at once. Third, AUC is simply the area underneath that curve. And finally, an AUC of 0.5 means the model is no better than random guessing, while a score approaching 1.0 means you've got genuinely strong separation between your classes, and evaluates overall quality, not just performance at one tiny snapshot. Techie is making one final appearance to help us sign off. So that is ROC-AUC and how it directly builds on everything from our precision and recall explainer to give you a complete picture of your model's true power. If you want to see this compared across real model types, drop a comment with the word ROC down below. And I'll leave you with this one thought. Does your current model look more like a top left bow, or is it just a machine learning coin flip? Make sure to subscribe for more explainers just like this one. Catch you in the next one.